Okay, so here we are, Wednesday the 23rd, it looks like. So we were scheduled just to do 3.2, but I'm actually up to 3.3, so I'm a little bit ahead. 3.1 I got rid of very quickly, of course. Well, it's nice to be ahead in case I fall behind a little bit later. Okay, yeah, Maxwell, did you have a question about something, please?
Yeah, it's about Unit 4. We also don't have a 4.1.
Same thing, right. It's all throughout. When I originally had this, there was 4.1 and whatever. You're right, it doesn't exist, so that means we have extra days there, evidently. So, yeah, don't worry about that. So, you're right. Anytime there's a section one, it doesn't look like I put it anywhere else, so maybe I just goofed there, but whatever. Okay, so we're a little bit ahead, which is fine. And so we are here, 3.3. And yeah, it's nice to get ahead in case something wrong goes again, as happened to me. As you already know, I was gone for a week. I didn't really go anywhere. I just had no internet. Okay, so if we can get ahead, we will. In other words, I'm not just going to stop and say, oh, we're a day ahead, let's just take a vacation. No, we're not going to do that. We're going to keep going, especially the way we are now in case something goes wrong. All right. Okay, getting back to where we were last time, we were doing polynomial long division. And the last thing we had mentioned was, okay, we did this polynomial long division. The remainder came out to be 11 if I divide it by x minus 2. And then I plug in a positive 2, not a negative 2, a positive 2. You either think of changing the sign, or the game you can play also is, what number do I plug into this to make it 0? Well, 2. It turns out if you plug in 2, you get 11, which happens to match the remainder over here. Likewise for number 3, if I divide it by x minus 1, there was no remainder, which means if I plug in 1, p of 1, you plug in 1, 1 cubed is 1, 1 squared is 1, minus 2, 1 plus 1 minus 2 is equal to 0. Okay, so that gives us something called the remainder theorem now. The remainder theorem, when a polynomial p of x is divided by x minus a, then the remainder equals p of a. Okay, so you change the sign of this. So that means if this is a plus, this would be a minus. If you do a polynomial long division, there's two ways to get the remainder. One way is to actually do all this stuff. Okay. The faster way, sometimes, is to find p of a. Just plug in. I say sometimes that's faster, sometimes it isn't. Okay, that also leads us to something called the factor theorem, which is an application of this. Factor theorem, if p of a equals 0, i.e. the remainder is 0, then x minus a is a factor of p of x. So that's what happened over here. Since there was no remainder, I can now say that x minus 1 is a factor of the original polynomial, okay? Because the remainder was 0, because when I plugged in the a, I got 0. So by plugging in 1, you get 0, so x minus 1 turns out to be a factor. So that's something called the factor theorem. Show it to you also in the text. It's on the top of 148, the factor theorem. If a polynomial p of x is divided by the linear factor x minus c, the remainder is p of c. Okay? And notice again the sign change. If you're dividing by x minus c, you plug in positive c for the remainder. So if you're dividing by x minus 2, here you plug in 2. Right? Here we divided by x minus 2. But for using the remainder theorem, we're plugging in 2, not negative 2. So essentially you change the sign. Okay, the linear term x minus c is a factor of the polynomial p of x if and only if p of c is equal to 0. That's saying the same thing, right? That if the remainder is 0, then by definition you have a factor x minus c is a factor. Okay, so that's what we're using here. So here it is, if p of a equals 0, then x minus a is a factor of p of x. If you want, you can put this on your cheat sheet. Maybe for some of you, you do the homework problems, you kind of get the idea, and you say, okay, I know what's going on. I don't need to write it on my cheat sheet. That's perfectly up to you. Okay, so now what are they saying for something like question 7? they're saying P of x equals blah, 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 x cubed minus 5x squared plus 8x minus 4, and the C is equal to 1. Okay, so let me show it to you. Use the factor theorem to show that x minus c is a factor of P of x for the given value of c, and then factor P of x completely. Okay, so one of the key things we're going to try in this section is to factor this whole thing out. Okay, so 7, 9, and 11 are like that. I'll do 7 right now, and maybe do another one. Okay, c equals 1. So I could do the polynomial long division. I will in a second. But we're trying this theorem of plugging in 1. Okay, so plug in 1. 1 cubed is 1. 1 squared is 1. So it's easy to plug in 1. So it's 1 cubed minus 5 times 1 squared plus 8 times 1 minus 4, which is 1 minus 5 plus 8 minus 4. That's equal to 0. So when I plug in 1, I get 0. Therefore, x minus 1. X minus 1 is a factor of P of x. So in other words, when I divide this polynomial by x minus 1, I should get no remainder. Okay, and let's actually show that now. So now I take the x cubed minus 5x squared plus 8x minus 4 divided by x minus 1. Okay, yes, the answer is already there, but let's pretend we don't see it. So how do I do the long division, right? First thing here, first thing here. What do you multiply x by to get x cubed? X squared. X squared. Now take x squared times this whole thing. X squared times x, x cubed. X squared times negative 1, negative x squared. Subtract. Remember, it's a subtraction, so that'll lead to double negatives. X cubed minus x cubed is nothing. Negative 5x squared minus a negative x squared. That's negative 5 plus 1, negative 4x squared. Bring down the 8x. Start over. Okay, so first thing here, first thing here. What do you multiply this by to get this? How do you go from x to negative 4x squared? Multiply by negative 4x. Now take negative 4x times this whole thing. Negative 4x times x, negative 4x squared. Negative 4x times negative 1, positive 4x. Subtract, so minus parentheses. Negative 4x squared plus 4x squared is 0. 8x minus 4x is 4x. Bring down to negative 4. Do it again. First thing here, first thing here. What do you multiply x by to get 4x? 4. X squared minus 4x plus 4. Okay, now take 4 times this whole thing. 4 times x, 4x. 4 times a negative 1, negative 4. Subtract. Well, we already know that anything minus itself is 0. So there's no remainder, which is what we expected. Okay? If x minus 1 is a factor, then that means when I do the long division, I get no remainder. And there is no remainder. All right, so now I can say that this original polynomial, x cubed minus 5x squared plus 8x minus 4, I can write as x minus 1 times x squared minus 4x plus 4. And I'll show you that back up on top now. X minus 1, x squared minus 4x plus 4. And then we go ahead and factor this. Oh, that's not that hard. We already know how to factor that, right? What two numbers have a product of 4 and a sum of 4? Well, 2 and 2, both signs being negative. So it's x minus 2, or x minus 2 squared. All right, so I've completely factored this original polynomial, which is usually the name of the game right now. Okay, so they're going to give us some polynomial, like third degree, whatever. Can we factor it all the way? In this case, yes, we can. X minus 1, x minus 2 squared. Okay. And then just for practice, I put up a little graph here, so let's review the graph. So the zeros are 1 and 2 of multiplicity 2, right? That 2, so we say multiplicity 2. This is multiplicity 1. And if you're still bothered by this multiplicity thing, there's one way you can think of this is x minus 1, x minus 2, x minus 2. right? That square means there's another x minus 2, right? So if I wrote x minus 1, x minus 2, and another x minus 2, then I would read off what are the zeros? Well, 1, 2, and 2. Well, you said 2 twice, so that's the reason why we say it's a multiplicity of 2. All right, so lay these two down. Now you notice I didn't make any number chart, but I don't think I have to. Okay, let's talk quickly about end behavior. End behavior means to the right of 2, to the left of 1. Okay. Now, calculation is much easier here. Tell me something about x minus 2 squared. If I plug in anything besides 2, that'll give me 0, right? If I plug in anything else because it's squared, it's always going to be what sign? Always going to be positive, right? So since this is always positive, the sign can just be determined by that. Okay. So what do we get when we plug in 3? 3 minus 2 positive, shoots to infinity. How about on this side? 0. 0 minus 1, negative 1, negative. Goes down like that. And then over here, I will use the rule that x minus 1 is multiplicity 1. So if you have a multiplicity of 1, it always goes across the x-axis. So since at this stage of the game, okay, I got this, I got this. I know that side shoots to infinity. This side shoots to negative infinity. And x minus 1 has a multiplicity of 1, so it crosses the x-axis. So since this side was below, this side is above. Okay. So there's a quick graph of that one. It goes like so. All right, number 11 is a little bit harder because the numbers are not as nice. P of x is equal to blah, blah, blah. They want you to plug in 2/3. Oh boy, so how do I do 2/3? 3x cubed plus x squared minus 8x plus 4. C is equal to 2/3. Okay, so I plug in 2/3, so it's a lot of fractions. So P of 2/3, P as a polynomial function. So 3 times 2/3 squared, cubed, plus 2/3 squared, minus 8 times 2/3, plus 4. Okay. All right, what's 2/3 cubed? 2 cubed, 2 times 2 times 2, 8. 3 cubed, 3 times 3 times 3, 27. And by the way, 3 and 27 cancel, leaving me with 8 over 9, right? Okay, then 2/3 squared. 2 times 2 is 4. 3 times 3 is 9, so 4/9. Minus 8 times 2, so 16/3, plus 4. Okay, so this is 8 over 9, 4 over 9, minus 16 over 3, plus 4 over 1. So it looks like a good common denominator is 9, right? So that's already 9, that's already 9. 3 and 16, so multiply top and bottom by 3, 3 over 3, and 9 over 9. So 8 plus 4 minus 3 times 16 comes out to be 48. 4 times 9 is 36. Okay, and do the top. 8 plus 4 minus 48 plus 36. You can punch in your calculator. That's 0. And 0 divided by 9 is 0. Okay, so x minus 2/3 is a factor of P of x. Okay, but I don't think I want to use x minus 2/3. Okay, so there's a little trick that we're going to do. Okay, so I don't want to have the fractions. Okay, since there's a 3 here, I can make the problem easier, and there's a 3 here. How about if I multiply by 3? 3 times x minus 2/3 is 3x minus 2. So I would rather divide by 3x minus 2. Okay, so 3 times x is 3x. 3 times a negative 2/3, 3's cancel out, so I have 3x minus 2. So 3x minus 2 is a factor of P of x. That makes things a lot easier on me. Okay, see, I don't want to divide by that. I get all these fractions all over. But this should be nicer. Okay, so let's try the polynomial long division on this one. And yes, you already see the answer, but pretend it's not there. Okay, so how do you go from the first thing here to the first thing here? 3x cubed. So what do you multiply 3x by to get 3x cubed? That's x squared. Okay, x squared. Now, x squared times this whole thing. X squared times 3x, 3x cubed. X squared times a negative 2, negative 2x squared. Subtract. So it's always minus parentheses. This drops out. Okay, watch out here. X squared minus a minus, so plus 2x squared is 3x squared. Bring down to negative 8x. Do it all over again. Okay, so first thing here, first thing here. So how do you go from 3x to 3x squared multiplied by x plus x? Now take x times this whole thing. X times 3x, 3x squared. X times a negative 2, negative 2x. Subtract. That's why it's always minus parentheses. Notice it's always minus parentheses, minus parentheses, minus parentheses. 3x squared minus 3x squared, nothing. Okay, watch out for all the negatives. Negative 8x minus a minus, so plus 2x, is a negative 6x. Bring down to 4. Start over. What do you multiply 3x by to get negative 6x? Negative 2. Now you take negative 2 times this whole thing. Negative 2 times 3x, negative 6x. Negative 2 times negative 2 is a positive 4. And you already know whenever you take anything and subtract itself, the remainder is 0. So there we go. No remainder. So this original polynomial, I can factor into that times that. So there we go. 3x cubed plus x squared minus 8x plus 4 is this factor, 3x minus 2, times x squared plus x minus 2. And now we can factor this just from algebra 1. Okay, I leave the 3x minus 2 alone and factor this. X squared is x times x. How do you get 2? Well, only 1 times 2. And the plus means the plus should go with the bigger number, which is 2. So finally, we have the whole thing factored. 3x minus 2, x minus 1, x plus 2. And that is that for that one. Okay, so I've shown you how to do stuff from here and stuff from here. Okay, so starting with problem 13, we now have something called the rational zeros test or rational root test. Okay, so let me talk about that. I'll show it to you in the book, and then I'll give you my version. Page 150. The rational zero test, sometimes called the rational root theorem. And I'll show it to you, my version, it will say the rational root theorem, same thing. Okay, so suppose P over Q is a rational zero of this polynomial. Okay, what's a rational number? It's a fraction, essentially. It's something of the form integer divided by an integer formally. Okay, so here's a polynomial, a n x to the n plus a n minus 1 x to the n minus 1 plus blah, blah, blah plus a1x plus a0. So the a's are the coefficients. Okay, so the x's are like x to the 5th, x to the 4th, x cubed, x squared, x, and constant. Okay. All the coefficients are integers. A n is not equal to 0. So the leading coefficient is not 0, because if this were 0, you would just throw it out. Okay. Then P divides A0, the numerator divides A0, the constant term. Q divides AN, the leading coefficient. The rational zero test provides a list of possible rational zeros. Okay, what they say is correct. You might not understand what it's talking about, so I'll give you my version of it. Okay, so the numerator is a factor of the constant. The denominator is a factor of the leading coefficient. Okay, and I'll show that to you in my version. Okay, so the book's version is correct. I'll give you my version. Move this out of the way for a moment. Okay, the rational zeros test, or sometimes called the rational root theorem. Given a polynomial p of x, if there are any rational zeros, they are of the form. So this is what it looks like. Plus or minus factor of the constant term divided by factor of the leading coefficient. Okay, this is what the book calls P over Q. Okay. If there's any rational numbers, rational zeros, the numerator is a factor of the constant term, the number way at the end. The denominator is a factor of the leading coefficient. They call that Q. And none of this makes any sense until you start doing some problems. Okay, so I'll get started doing some problems on this. Okay, so it's called the rational zeros test, sometimes called the rational root theorem. If you want to put this on your cheat sheet, you may. Or if you want to put this in your cheat sheet, you may. Okay, I personally like mine better, but obviously I'm biased. Of course I like mine better. Okay, but if you like this better, use it. Some of you might say, oh yeah, I know what I'm doing, I get it, so you don't have to write anything. Right? So you make a choice after I do some problems involving it, whether you want to use the book's language, which is correct, there's nothing wrong with it, or my language, which obviously I think mine is better, of course, since I'm biased. Or maybe you don't need to put anything down once you get the hang of it. Okay. So right now you're probably saying, I have no idea what you're talking about, so let me do something. So determine all possibilities for rational zeros. We're only getting candidates for zeros. Okay? We're not saying any of these are zeros, but if there are any zeros, they only come from the list that I'm about to show you. Okay, so what am I talking about? So 13. Okay, if you can't see 13, I got it right over here. X to the fourth plus 2x cubed minus x squared plus 3x plus 4 equals 0. Okay, so the only numbers you look at for right now are the leading coefficient, 1, and the constant term, 4. That means right now you don't care about any of the in-between things. In fact, the answer to this problem would be exactly the same if this one was a -5, and this one was a 20, and this one was a million. You would still have the same answers. All of these have to be integers, though. So no fractions, no decimals, no square roots, and so on. So the possible rational zeros are plus or minus a factor of the constant. So the constant is 4. Factor of 4 divided by a factor of 1. Okay, so what does it mean? What are the factors of 1? There's only 1, so I'm divided by 1. What are the factors of 4? Factors of 4 are 1, 2, and 4. All right, so that means now you take from the list any of these guys divided by any of these. Well, in this case, there's only 1, so I'm just dividing by 1. But if you divide by 1, you don't have anything. So my answers, the only possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4. Those are the potential rational zeros. Okay, so what are we saying? Back here, the only possible rational zeros out of infinitely many numbers, the only ones that might work are these 6, plus or minus 1, plus or minus 2, plus or minus 4. They're the only ones, quote unquote, running for office, as it were. Okay? So I don't have to try 7. I don't have to try 5. I don't have to try a half. I don't have to try 316 divided by 521. They are not going to work. Okay? Now, you have to be careful about the way the theorem works. Okay? That does not mean these are going to work either. They might work, they might not work. Okay? But we can say for sure that there are no rational zeros that are going to work outside of this list. It's just like, I don't know, like running for office. Okay, so if you're not running for office, you definitely won't win the spot. But even if you are running for office, you might not win. There might be others that are going to win, that are running for office that might win, right? So the only ones running for office, so to speak, are these 6. But none of them might work anyway. Okay? But I know for sure 5 isn't going to win. -1/2 isn't going to win. Okay? So that's what this is saying. So these are the list of the possible rational zeros. Okay? What's a rational number? It's an integer divided by an integer. Okay? So no square roots, no pi or e or any of those numbers. Okay, it might be better if I show you 15. This was a little bit, quote unquote, easy because the leading coefficient is 1. Okay, let me try for you 15 where the leading coefficient is different. Okay, so 15, 10x to the 5th minus 14x cubed plus 18x squared plus 6x minus 4 equals 0. Okay, so list of possible rational zeros. Number 15. All right, the only numbers you really have to look at are the 10 and the 4. Never mind about that or that or that. So the theorem says factor of the constant divided by factor of the leading coefficient. Okay? And all of these have to be integers, and they are. So in other words, inside here you can't have a fraction You can't have a pi. You can't have a square root of 2 or anything like that. These are all integers. All right, so the numerator is a factor of 4. Don't worry about the negative because you're putting plus or minus anyway. So just like the previous problem, the factors of 4 are 1, 2, and 4. This time, however, we have the denominator factors of 10. So what are the factors of 10? What goes into 10? 1, 2, 5, and 10. Okay, so how do I build my list? Okay, there's a systematic way of doing it, so don't do it haphazardly. Just take all of these one at a time. Start with 1. So I take 1, 2, and 4 and divide it by 1. After that, 1, 2, and 4 divided by 2. And if there's any duplicates, throw them out. Then I take 1, 2, and 4 divided by 5. And 1, 2, and 4 and divided by 10. Okay, so that's a systematic way of doing it. So just point or pick only one denominator and put all these guys. Okay, so if I'm dividing by 1, I got plus or minus 1, plus or minus 2, plus or minus 4. Dividing by 1 is easy, right? Now, divide the same numerators by 2. So all 3 of these guys divided by 2. And it's all plus or minus. These are all plus or minus. So plus or minus 1/2, plus or minus 2 over 2, plus or minus 4 over 2. Okay. But I cross off plus or minus 2 over 2 because what's 2 over 2? 1, it's already on my list. And I cross off plus or minus 4 over 2 because that's plus or minus 2. That's already on my list, so I don't have to write it again. So these aren't anything new. Then I take these same ones and divide them by 5. All right, so plus or minus 1/5, plus or minus 2/5, plus or minus 4/5. And none of these are already on my list, so I don't have to cross any of those out. Finally, divide them all by 10. So plus or minus 1/10, plus or minus 2/10, plus or minus 4/10. Now, why did I cross off plus or minus 2/10? Because 2/10 reduces to 1/5. That's already on my list. And why did I cross off 4 over 10? 4 over 10 reduces to 2/5. That's already on my list. So there we go. All right. So when I try the polynomial long division, the quote-unquote only numbers to try are these. Granted, that's still a big list. That's what? 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16. You only have to try 16. That's a lot less than infinitely many numbers, right? Okay. If I just showed you this, there's infinitely many things to try, but I've cut it down to only quote-unquote 16. Okay. Of course, that still sounds like a lot. But of course, if you do a computer program, you could certainly program a computer to do that a lot faster than 16 is not so bad compared to infinitely many. So the only things to try are these numbers from the list. Okay. Okay, 17 I'll show you, and it looks like I'm almost doing them all, but that's okay. I'm sure you don't mind. Okay, 17 starts off with fractions. Now, in order for you to do the rational zeros theorem, you must have integers, no fractions. Okay. So we have to get rid of the fractions by multiplying by something. Okay. If you can see that at all, I got it here. So the original for 17 was 3/2 x cubed minus 5/2 x squared plus 7x minus 4. So the rational zeros theorem says you have to start off with integers, and there's a very easy way to do that. How do I get rid of 2? Multiply both sides by 2. Then I get rid of the 2's. So 2 times that, 2 times that, 2 times that, 2 times that. So 2 times that. 2's cancel out, 3x cubed. 2 times that, negative 5x squared. Then 2 times 7x is 14x. 2 times negative 4 is negative 8 equals 0. Okay, so now this is the way that I want it. I have integer coefficients. Integers means no fractions, no decimals, no square roots. Okay, so what are integers? 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Stuff like that. All right, so list the possible rational zeros. So plus or minus factor of the constant divided by factor of the leading coefficient. That's what the book calls P over Q. That means plus or minus factor of 8 divided by a factor of 3. All right, what are the factors of 8? Let's see, there are 1, 2, 3, there's 4 of them. Can you think of the 4 factors of 8? 1, 2, 4, and 8. And then divided by the factors of 3. What are the factors of 3? 1 and 3. Okay. So here we are. Plus or minus 1, 2, 4, 8 divided by 1 or 3. Okay, so how do you do it systematically? Well, just go one by one, cover up the 3, and I'm dividing by 1. So 1, 2, 4, and 8 divided by 1. Well, if you divide by 1, you just leave it alone, right? So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay, so I divided by 1. Now I divide by 3. So the same numerators divided by 3. So plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3. And there are no duplications, so I just have to literally write them all. So those are the only possible rational zeros. Now, again, these 16 numbers, right? 4 and 4 is 8 times plus or minus 2 is 16. We're not saying that any of these work. Maybe none of them work. But they're the only candidates. They're the only ones running for office, so to speak. So I don't have to try 5. I don't have to try 3 or negative 3. They're not on this list. They are not going to work. Okay? They aren't going to win, so to speak. Now, these still might not win anyway. None of them might win. Okay? But those are the only things to try. All right, so that's called the rational root theorem or the rational zeros test. Okay, and now find all rational zeros of the polynomial, then determine any irrational zeros and factor the polynomial completely. Now, the only way you're going to get irrationals is if you can get it down to a second degree quadratic, and then you could use the quadratic formula. Right? We know that. Okay, so I'll show you a couple of these, and maybe that'll be it. What time is it? 15 to? Okay, so 19 seems to be the easiest, and these get a little bit tougher, of course, but we'll see what we got to do. All right, x cubed minus 3x squared plus 4. All right, I happen to notice that when you plug in -1, you actually get 0. Okay, how do I know that? I just try it. Plug in -1 here, -1 here, -1 here. And besides, I see a 1 and a 3 and a 4. I know that 1 plus 3 is 4, and that would match that. So if I can somehow get this to be, the stuff behind my pen, if I can get that to be a -4, when I add it to 4, I get 0, right? And I see a 1 and a -3, so that made me think of -1. Okay? So I plug in -1. -1 cubed minus 3 times -1 squared plus 4. -1 cubed is -1. Okay, right here you got to be a little bit careful. -1 squared is 1. Times -3 is -3. Okay, it works. -1 minus 3 plus 4 is equal to 0. So that means x plus 1 is a factor of p of x by this factor theorem. Okay, so again, I plug in -1, I get 0. That means x plus 1, not x minus 1. X plus 1 is a factor. And one way you can verify that, of course, is to actually divide. If I were to divide by x minus 1, you'll see that there's a remainder. Let's divide by x plus 1. So x cubed minus 3x squared plus 0x. Remember we talked about the 0x, right? There's no x there. So 0x plus 4 divided by x plus 1. Cover this up temporarily. All right, first thing here, First thing here. How do you go from x to x cubed? Multiply by x squared. Now x squared times this whole thing. X squared times x is x cubed. X squared times 1, cover it up, I've already shown it to you, but anyway. X squared times 1 is x squared. Subtract. X cubed minus x cubed is nothing. Negative 3x squared minus x squared is a negative 4x squared. Bring down to 0x. Start over. First thing here, first thing here. How do I go from x to negative 4x squared? Multiply by negative 4x. Now take negative 4x times the whole thing. Negative 4x times x, negative 4x squared. Negative 4x times 1, negative 4x. Subtract. Negative 4x squared plus, right, double negative, plus 4x squared is 0. 0 minus a minus 4x, 0 plus 4x, 4x. Bring down to 4. And do it one more time. First thing here, first thing here. What do you multiply x by to get 4x? 4. Positive 4. I should get no remainder. Is that true? 4 times x, 4x. 4 times 1 is 4. Subtract. You don't have to bother. You know it's going to be 0. Anything minus itself is 0. It's just like when you did long division of numbers. If you got 7 minus 7, you know it's 0. So anything minus itself. All right, and we know how to factor that, right? So this polynomial, x cubed minus 3x squared plus 4, now factors into that times that. So x plus 1, x squared minus 4x plus 4. That's easy to factor. So there we go, x plus 1, x minus 2 squared, final answer. Okay, so I have completely factored this polynomial right over here. Okay. Okay, then let's see, 21, and then maybe I'll stop with 21. Okay, factor completely 2x to the fourth minus 3x cubed minus 3x squared plus 2x. Okay. All right, so factor this. 2x to the fourth minus 3x cubed minus 3x squared plus 2x. Well, I noticed that they all have an x, so that's easy. So take out the x. So that part's done. 2x cubed minus 3x squared minus 3x plus 2. Okay. At this stage of the game, I need to try to solve this for 0. So I'll play the rational zeros game. Okay. So the only rational numbers to try, the nice numbers, possible rational zeros, plus or minus a factor of 2 divided by plus or minus a factor of 2. Okay. So constant term factor divided by leading coefficient factor with both 2. The only factors of 2 are 1 and 2. All right, so the possible zeros are either 1 and 2 and divided by 1, or 1 and 2 and divided by 2. So take 1 and 2 and divided by 1, plus or minus 1, plus or minus 2. Then take 1 and 2 and divided by 2, plus or minus 1 over 2, plus or minus 2 over 2, but 2 over 2 is the same as 1. That's already on my list. Okay, so there are, quote unquote, only 6 numbers to try. Plus or minus 1, plus or minus 2, plus or minus a half. No other rational numbers work. So 5 isn't going to work, 21 isn't going to work, negative 80 isn't going to work. The only ones to try are these. Now these might not work either. They still might not work, but they're the only ones that are in the running, so to speak. Okay, by the way, you can usually tell by plugging in 1, all right? So if you plug in 1, you're just really looking at the coefficients. 2 minus 3 minus 2 plus 2, that's not going to be 0. But maybe because there's some similarity, that's why I try negative 1. Okay, I think negative 1 does work. Okay, so plug in negative 1 here, 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 and here. So P of negative 1 equals, that's an equal sign there. All right, so 2x cubed, 2 times negative 1 cubed minus 3 times negative 1 squared minus 3 times negative 1 plus 2. All right, so let's see, 2 times negative 1 cubed. Negative 1 cubed is negative 1, times 2 is negative 2. Minus 3 times negative 1 squared is 1. 1 times negative 3 is negative 3. Then negative 3 times negative 1 is a positive 3 plus 2. And lo and behold, that does come out to be 0. All right, so when I plug in negative 1, I get 0. So again, that means x plus 1 is a factor. So I'll do the long division. 2x cubed minus 3x squared minus 3x plus 2. So what am I factoring? I'm trying to factor this one now. So this divided by x plus 1 should give me no remainder. And here we go. So same thing. How do I go from here to here? Multiply by 2x squared. Now take 2x squared times this whole thing. 2x squared times x, 2x cubed. 2x squared times 1, 2x squared. Subtract. That minus that is nothing. Negative 3x squared minus 2x squared minus 5x squared. Bring down to negative 3x. Start all over. First thing here, first thing here. How do you go from x to negative 5x squared? Multiply by negative 5x. What is negative 5x times each of these? Negative 5x times x, negative 5x squared. Negative 5x times 1 stays negative 5x. Subtract. Negative 5 minus a minus 5, that's negative 5 plus 5, 0. Negative 3 minus a minus 5, negative 3 plus 5, 2x. Bring down to 2. One more time. How do you go from x to 2x? Multiply by 2. 2 times this whole thing. 2 times x, 2x. 2 times 1 is 2. Subtract, you know there's going to be no remainder, which is what we were anticipating. We expected that. So we have this, no remainder. So this thing now factors into that times that. All right, so way back at the original, I already took out an x, and I now take out an x plus 1. So now the original polynomial is x times x plus 1 times 2x squared minus 5x plus 2, and now that's a simple factorization. So leave this alone, x plus 1, paren, 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 paren. 2x squared has to be 2x times x. A minus and a plus means these are both minuses. And then in order to get the negative 5, the 1 should go here, and the 2 should go here. You can double check by folding it back out, right? 2x squared minus 4x minus 1x is minus 5x plus 2. All right, so we have completely factored the original. Okay, so we have this original polynomial is equal to x times x plus 1 times 2x minus 1 times x minus 2. And that's about it, and we're done. All right, so that'll do it, folks. Let me stop the share and check the chat. There's nothing in the chat. Okay, so anybody have any quick questions? And if not, we're done. Okay, I don't hear anything, so that'll do it for today, folks. All right, so have a good day. We'll see you tomorrow. Okay, bye, everyone.